Alhamdulillah, assalatu wassalamu ala rasulillah. Assalamu alaikum wa rahmatullahi wa barakatuh. One of the toughest topics to be considered in physics is charge distributions and electric field due to charge distributions. Today we are going to discuss charge distributions and their electric fields around them at a certain point, and that field can be calculated by following certain steps, specific steps. And if we understand these steps, and this is just a procedure, and if we understand this procedure, then we can easily calculate electric field due to any kind of charge distributions. But let me explain briefly what are charge distributions. There are two types of charge distributions: charge distributions. One of the charge distribution is random. What random means? Random means if you have an object, suppose this a sheet, there is a charge plus, there is two charges, there is one charge. This is not uniformly distributed throughout. That means in some area there is more charge and in some area there is less charge. This kind of distribution is known as random charge distribution. And there is another kind of distribution which is known as uniform or uniformly charged distribution. What it means, suppose you have a same sheet. In this, if you observe, you will find charges throughout the whole surface uniform. That is, in any particular region or area, there is equal amount of charge present if the areas are equal. This kind of distribution is known as uniform charge distribution. This uniform charge distribution could be further divided or subcategorized into three categories. One is known as linear charge distribution. What it means? It means that there is a thin or there is a line, and in this line there is charge distributed throughout the length. Second is surface charge density. And what is surface charge density? In a given surface there is uniformly distributed charge. And another is volume charge distribution. Suppose this is a sphere, and on this sphere there are charges distributed uniformly throughout the volume. In each case, we can assume that Q charge is distributed throughout the length L, and in this we can say charge Q is distributed throughout the area A of the surface. And in the third case, charge Q is uniformly distributed throughout the volume V of the sphere or any solid. And we define a quantity Q by L in this first case. What it means? It means if we select a unit length, say 1 meter or 1 centimeter, then in that unit length amount of charge present is Q by L, and this is denoted by lambda, and it we call linear charge density. Linear charge density. In the similar manner, we can say charge Q is uniformly distributed throughout area A. So we say this charge Q is uniformly distributed in the area A. If we take unit area, then what is the amount of charge present in that unit area? That is Q by A, and this is known as surface charge density. Surface charge density. So here we can write it surface charge density. And what about that solid? Here the similar concept, Q divided by V. What this says? It says that in total volume B, charge Q is uniformly distributed, and Q by V gives amount of charge present in unit volume. and this is represented by the letter rho, and this quantity is known as volume charge density. Volume charge density. So if we have a uniform charge distribution, it may fall into one of the three cases. If there is only a length, that is, it has no width, no thickness, only a length L, in this case the charge density is known as linear charge density, Q divided by L. If we have a area, thin area, that is, it has only two dimensions, length and width, it has no thickness, then this quantity Q by A gives us surface charge density, and in this case we have three dimensions, length, width and height, and in this case we have a volume charge density given by Q by V. Obviously, for different charge distributions we have different units. For example, here we can see in numerator there is charge, and unit of charge is coulomb, and unit of length is meter. Therefore, it will have a unit of coulomb per meter. In similar way, we can calculate the unit of surface charge density, coulomb meter square per meter square, and here coulomb per meter cube. If we understand these charge distributions, then we can move or proceed to calculate electric field created by these charge distributions at different points. So the technique to calculate electric field from any kind of distribution or charge distribution is simply to use the formula or expression E equals 1 upon 4 pi epsilon naught Q by R square. And we know that this electric field is being created by a charge Q, and we are calculating electric field due to this charge at a distance R, say at a point P. So here this term 1 upon 4 pi epsilon naught is a constant term, and this reduces to E proportional to Q by R square. What we have electric field which depends on two things: charge from which or about which we are talking, which is creating the electric field, and distance, at what distance we are calculating that field. If we increase the distance, then electric field is decreasing or will decrease, and similarly if we increase the charge, electric field will increase. So this is the most important thing to consider or to remember. Now focus on a linear charge density. This is a linear charge density. It has a length L and a charge uniformly distributed on this length L. So if we want to calculate at a point P the electric field, what we need to take a small width of this length, call it dl. The whole charge is Q, so the width dl will have a charge, say dq, and we know this dq charge will be given by lambda dl. Why? Because lambda, as we have defined, lambda equals q by l, that is, this is the amount of charge in unit length. This is the amount of charge in unit length. It means if we have a length dl, then total charge on this dl will be equal to lambda times dl, and we can have dq equal to lambda dl. Now we want to calculate electric field at a certain point, say point P, and this point can be anywhere, here, here. It is a general way, it is not a particular way, and we can also have particular cases, but we are not restricted to calculate only at a particular point. We have many different points, and we can calculate at any point if we know this technique. So what we are going to do, we are going to calculate electric field, and electric field due to a small charge dq will be small de, and according to definition or this expression we have 1 pi 4 pi epsilon naught q, and in place of q we can write dq by r square, and this r is the distance. And remember one thing, this r is variable as I have already described it. So what we need to substitute dq we can write it lambda dl, and if we substitute this we get 1 upon 4 pi epsilon naught lambda dl by r square. And in this expression we can see that 1 upon 4 pi epsilon naught is constant, lambda is also constant, and we are left with dl by r square. So if we want to calculate total electric field, then we need to integrate this expression, and here we can say if lambda is taken out, lambda upon 4 pi epsilon naught, we are left with dl by r square. This is the quantity which is a variable quantity, and if we can substitute some proper arrangement or values of this from the symmetry, then we will have complete electric field. And in similar way, for surface charge density we will have here sigma upon 4 pi epsilon naught dA by r square. This r is also a variable. We just need to find what is dA and what is r, how it is related to dA. If we make that substitution, we can easily calculate this with proper limits. In the same way, if we have a volume charge distribution, then this expression become rho divided by 4 pi epsilon naught and small volume dV by r square. With proper limit we can calculate this. So whenever there is a charge distribution, we don't need to think that it is tough. We just need to find a proper substitution, proper limits which when integrated gives the result. So main thing is not to calculate the electric field. Main thing is to understand that what this element looks like in mathematical form, which we can integrate with proper limit. In the similar way, we have three similar expressions, and this is the simple technique. If we know this thing and the limits, we can easily calculate, and that will be discussed in a separate video, and I will take particular examples and I will try to explain how to choose these area or volume and how to relate these to the distances or variable distances and what limit should be taken, so that we have a particular expression for a particular distribution at a particular point.